humanity evolves, and that is genetically. We have generations, and then those generations have the next generation, right? We are not the first generation to inhabit the earth, right? People have been around for hundreds and hundreds of thousands of years and evolving over that period of time. And hopefully, the idea is that people are getting better and better, smarter and smarter, although it's debatable. But I think by and large, I think we certainly are smarter than our predecessors, hundreds of thousands of years ago. And maybe even more so than our predecessors, thousands of years ago, or maybe several hundred years ago. We're getting more adept at certain things and smarter and more clever, able to solve more difficult problems. So we can say that we're improving, we're evolving. So that's the idea. So genetic algorithms, and I'm not going to do the lecture on that, but genetic algorithms essentially involve an element of randomness. So we're going to create randomness. We're going to try to basically say, I don't know what is the best solution for 100 cities. I don't know. But here's my guess, and I'm going to pick a permutation of 100. I'm just going to pick it. So I'm going to take 100 numbers, 1 through 100, and I'm going to pick at random the numbers, and I'm going to put them into a sequence. And that will become my guess. And I'll do this 2,000 times. So I'll take 2,000 guesses. Well, any one of those is essentially a random guess, right? In order to create a genetic program, we need to have an encoding for our solution. And the encoding, we basically said, was an array, if you will, of a permutation of the numbers 1 through n, where n is the number of cities. It's a permutation. Any one. One of those permutations is the best. Which one, I don't know. I'm going to make, so the encoding is a permutation of 100. First 100 integers. How can I evaluate how good an answer is? How long does it take to evaluate an answer? It doesn't take a lot to generate the guess. I just generate 100 random numbers. Well, it's not quite easy as that. I really need to pick the permutation of 100. So it's not that difficult to do that. How long does it take to test how good my solution is? That's also very easy. Just go from the first city to the second city. We'll have a matrix that tells distances from A to B. So from here to here is this distance. Then from here to here is this, add it. So basically we'll have if I make 2,000 random guesses, I'll have 2,000 distances for cycles, right? I'll have 2,000 random guesses for cycles. Some of them are going to be very good. Oh, I shouldn't say that. Some of them are going to be better than others. Some of them could be unbelievably bad. Because they're going to go. It's crazy because they're random. And there's 100 of them, so they can go anywhere. And some of them are going to be better. So what we're going to try to do is we're going to take those encodings, those 2,000 encodings, and we're going to make parents out of them. And what we're going to do is we're going to take, let's say we're going to take a random encoding and another random encoding. We're going to say, okay, you guys are going to be the parents. You're going to generate 2 children. What's a child? A child is another encoding. It's another guess. But what we're going to do is we may take like half of the encoding of this one, half the encoding of that one, and that's going to be the new encoding. Of course, that's really not so simple. Because if you have 100, you cannot have any cities from here to here. They cannot be, so we have to be clever about how we produce children from the given encodings. Sometimes it's really, really easy, and sometimes it's a little bit more complex. For this particular problem, it's a little bit more complex. Because basically, if I take the first 50, then the first 50 from the first parent is going to be fine. But the second 50 from the second parent is bound to have some problems. Because if you visited any of the cities in the first sequence, you cannot visit them in the second sequence. So the second sequence, in a sense, has to have some changes. You cannot take it exactly. So we might have to modify some. We could take like this. We could take 10 from the first, 10 from the second, 10 from the first, 10 from the second, like this, alternate, do this 5 times. We need to have a method of creating the next generation, and from 2 parents, we're going to create 2 children. We call this process a crossover. So we'll generate a random sequence. Typically, we can evaluate them by evaluating the best to the worst. Some of them are going to be so bad, we're going to wipe them out. We're going to say, that's awful. And what we're going to do is we're going to say, okay, these are all my guesses. These are the 15% of the worst ones. I'm just going to eliminate them. I'm going to take 15% of the best ones. I'm going to duplicate them. Then I'm going to randomize it. Then I'm going to choose random values to be parents and from each two parents, I will produce two children, we'll call the next generation. I will do the same thing again. I will evaluate them, throw away the bottom 15 perhaps, randomize them, and go to the next generation. And I'm hoping that I will be decreasing my distance for the cycle, because the quality is based upon the smallest distance. What's the minimum distance? Well, that's an algorithmic solution. I don't know what the minimum distance is. But that's the idea. So as long as there's an encoding for a problem that's hard, then genetic algorithm is a good approach to try to solve it. There are different approaches. So genetic algorithm is one class of heuristics. Another one is called neural networks, deep learning, neural nets. Those are all techniques to get some insight into hard problems. I'll give you another example. Here I am talking about it, like I said I wasn't going to. But I'll give you one more example. This is a very famous, so there are tremendous amounts of these very so-called hard problems. So I'll show you another sort of a very classic problem. So you don't have to draw this because you'll never draw this correctly. Even I won't draw it correctly because I'm just randomly doing it. So I don't know what I'm doing. So basically what I'm doing is I'm partitioning a space into non-overlapping segments. Looks very nice, right? So this problem. So now, how would you represent this from a computer standpoint if you had to represent this structure? What kind of data structure is this? It's a graph. You can represent it as a graph. So basically, if you look over here, we could basically from here make a connection to here, connection to here. So if we numbered them, we could see that node 1 has a connection to 2 and also to 3. So we could actually, so whenever there's a connection, so you understand, so we could easily do this as a graph if we wanted to. Okay, so now there's a problem called the 3-color problem. So we need to create, number one, a graph for the problem. And so you understand how that would work. We create a graph based upon this with all the nodes and all the connections. Some nodes have one neighbor, some 2, some 3, some 4, maybe there's some 5. I don't think much more than that, although we can make this different. So we need to have a graph for the problem. So the graph could look something like this. So this is 1, let's do over here, 2, 3, 4, 5. I suppose it would look something like this. Node number 1 has a connection to 2 and 3. So it would look like this, right? And node number 2 has a connection to, what do we have? 1, 3, 4, 5. 1, 3. I'm keeping them in order. Okay, and et cetera, right? We can do the whole thing. So basically, so I might be interested in finding out whether or not a node is adjacent to any other node. And then I'm going to have another graph, or another array rather, I should say, which is going to be an array, let's say there are n total nodes. So let's say this is going to be n, this is going to be 1. And then here we're going to have this is going to determine what color one of those partitions, one of those nodes are. So the 3-color problem basically says, is there a solution, or find me a solution to color this graph so that no 2 adjacent nodes have the same color? Is there a solution? Well, it's not obvious. We have 3 colors. You cannot, so for example, if this is blue, then none of my neighbors can be blue. You understand the problem, right? So this problem, so the question is, how hard is this problem? Well, let's say there are, how many partitions do you think we have? 4, maybe we have, let's say 20. So we have 20 nodes. If we have 20 nodes, then essentially, and we're going to create a genetic algorithm for it, the number one thing we have to do is do what? What's the first thing we do for a genetic, to try a genetic solution? We have to create a what? Random number, but we have to have a meaning to it, so we have to have an encoding. The first encoding for the problem when we wanted to have the shortest cycle, we had a permutation of the first 100 integers, or the first n integers. Here, we don't need a permutation, but we have 20 nodes. So what we need is to get a random encoding, or random solution, we're going to create a vector, and this vector is going to have, it's going to have 20 elements in it. And each element here is going to be either, we're going to randomly give it a value of RGB. Red, green, and blue, 1, 2, 3, whatever you want. Basically, we can only put one of 3 values in here. So for example, okay, so how long does it take me to do this? Very, very easy, right? Very, very easy. So basically, I could do, now first of all, how many different encodings are there? Well, this is an encoding of a solution. How many possible choices do I have in this location? 3. And the next one? 3, 3, 3. They're independent. It's different than the previous problem where basically if you visited city 5, in your vector you couldn't have another 5 reoccurring. But here we can have 3 choices, 3 choices, 3 choices. They're all independent. I mean, one possible very bad guess is to make everything blue. Blah, 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 blah. I'll give you a clue. It's not going to be a solution. Or green, 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 green. Okay, so that's not going to be a solution either. So what we're going to have is we're going to have, so the question is how many possible solutions are there to this 3-color problem and what makes this problem hard? Well, basically, what is the complexity? What is how many possible solutions are here? Well, there's 3 times 3 times 3 times 3, 3 to the power of 20. So let's do that right now. Let's see what I get. So I'm going to take 3 and raise it to the power of 20. And that gives me, well, 3,486,784,401. We said, well, that's a big number. It's a big number. It's not overly big. But what happens when I increase the number to 100? Well, if I increase it to 100, it's going to be 3 to the power of 100, and that's going to be bigger. Let's see if we can get into the big size. Yeah, now we're playing a game here. This is 5.15 times 10 to the 47th power. So if I had 100 components, basically what I'm telling you is there's no way to find an answer in our lifetime. Or in your children's lifetime. Or in their great-great-children's lifetime. So it's going to be a very hard problem. But to generate a guess, and we can of course extend this to 100, is really, really easy. Because I can just randomly put these things in here, and then what I'm going to do is I'm going to take this, and I'm going to find out basically whether in this graph I'm okay. So 1 is going to have a color, right? So I'm going to look at the color of 1, which is red, the color of 2, which is green, and the color of 1 against 3, because they're neighbors. And they are, so far so good. So that's how I'm going to check. So you see the checking is very easy. Randomly selecting is very easy. So, but I'm not going to have just one of these. Maybe I'll end up having, for example, 20,000 of these guesses. Some of them are going to be better than others, again. And then I'm going to need to create the next generation. So in that case, what I'm going to do is I'm going to create the crossovers. And the crossover could basically cut it someplace around 50. And then for the next generation, take the first 50 with these 50, generate the next generation. And then reverse it, take this one, match it with this one over here. The idea is you want to keep the good ones, drop some of the worst ones, and you're hoping that some of the good pieces of the good ones and the other good ones can match up. I mean, maybe you have a really strong solution here, and a really strong solution here, but nobody has a good combined solution. So somehow when you combine these solutions, all of a sudden you're going to have, so how would you grade the quality of the solution? How do we grade the quality of the solution? Well, we'll probably grade the quality of the solution by an evaluation of determining how many violations do we have. The perfect solution, the correct solution, has 0 violations of adjacents being the same color. So for example, if I find that if I go through the whole graph, I find that 2 and 4 are the same color, and of course 4 and 2 are the same color, which by the way, you realize what I can do is basically I only need to go to neighbors that are bigger than me, never smaller than me. So once I go to nodes 50, for example, my only neighbors of interest are going to be neighbors higher than me, because everybody else lower than me who's gone to me has already gone to me. So that's just, a smart idea. So the basic idea is, and that means that if there's a violation once, you're not going to get it again. Because if 1, for example, connected to 50, and that was a violation, then 50 also is connected to 1, it also will be able, we don't need that. We need to double count it. So basically, so in a sense, we'll have a adjacency list, which is going to be for a non-directed graph. Because we can go back and forth, non-directed. We don't have direct directions here. Okay, and so therefore, if I find, for example, that I have a clash from 2 to 5, but nowhere else, what does that mean? Well, that's a lot better solution. It's a lot better solution than if I have 78 clashes. So that means I may be close. So I like that. So, anyway, so this is the basic idea. And so the key for genetic algorithm is always going to be find an encoding for your problem, generate random solutions with that encoding, evaluate them, drop the lowest, keep everything else, maybe replicate some of the highest, randomize them, produce the next generation. Repeat, 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 repeat until when? Until you stop. Repeat until you have something that you are happy with. And when you watch the video, you'll see I have a program that does this cycle. And you'll see visually, I have an actual graph that dynamically changes. You'll see the dots, and I'm trying to find the shortest path. And it does a pretty good job on my little small computer. It does a pretty good job for maybe up to 32 or even 64, which is very substantial. Because 64 factorial is a big number. Not as big as 100, but when you give it a really big number, then you start not having such great results. So you have to, again, try to see how you can improve these results. But we can still solve problems that would be computationally very, very hard to do otherwise. And so that's just a basic technique. Okay, so let me turn this thing on.